Okay, well, I think I might go ahead and get started. Okay, so what do we want to do today? Uh, so as the a- as I've kind of mentioned, today I want to start getting into what I might call some big kid physics, where so up to this point we've dealt a lot with Newtonian mechanics, and it's good and it works, but it's somewhat limited in its structure, in that it's very dependent on the types of coordinates that we use. So what I want to do moving forward is start developing a system of classical physics, which will allow us to sort of move away from this sort of coordinate dependence. Um, and so the first place we're going to go with that is Hamiltonian mechanics. So the beautiful thing about Hamiltonian mechanics, as we'll see, is that we're allowed to develop it without ever having to consider a specific choice of coordinates, which means that in the future we might be considering a system where we might have to um, we might want to use a sort of special set of coordinates to describe it that might be really convenient to use, but in Newtonian mechanics might be clunky to get useful expressions from. So the first thing I'm going to end up talking about is, like I say here, some ground rules, specifically the types of coordinates or the types of systems. Sorry, that we actually will consider, because it turns out that this sort of coordinate independent formalism is trickier to do in some systems than others. So the first thing I want to talk about is the types of systems that we'll usually be considering. Um, then from that, we'll actually go into developing this coordinate independent formalism for classical mechanics. Um, so we'll jump into actually, starting from what we already know, getting to Hamilton's equations of motion. And then, kind of along the way, and I'm going to end up doing a very simple example at the end, we'll see the benefits of the freedom to choose these coordinates. So we'll see things popping up that were actually pretty difficult to get to in Newtonian mechanics, but they just sort of fall out of this coordinate independent formalism, which can be very helpful. Very helpful. So, with that said, feel free to post questions in the chat. I try to keep my eye on it. There's a few things in there already. And so, yeah, feel free to ask any questions. I tend to take breaks and answer those questions. Or, yeah. So, yeah, just to address a few things in chat. The action angle variable, I'm not exactly sure what you mean by that, but this has nothing to do with the action. We're never going to talk about action with Hamiltonian mechanics. And actually, there's a very specific reason why I don't want to talk about actions. Usually in a undergraduate course, you'll start by learning Lagrangian mechanics and then go on to Hamiltonian mechanics. But I feel Hamiltonian mechanics, based off of what we already have done, is much more motivated. There's very little motivation right now to look at actions and Lagrangians and things like that. So that's why I'm choosing to cover Hamiltonian mechanics before even touch Lagrangian mechanics. Working with this in my uni studies. This is something that I've done previously and have looked at quite a lot since then. So, yeah, okay. That it's to the questions. Let's get going. So, okay. Previously, we looked at we've already sort of looked at a case where we used this sort of general coordinate formalism without even really knowing that we were doing it. So in particular, we looked at we used it a lot when we were looking at harmonic oscillators, coupled harmonic oscillators specifically, and the wave equation. So, for example, just to sort of get an idea of what we're trying to do, when we looked at that case, we had, say, some masses, and they're all attached to each other by springs. And we found that it was very, very inconvenient to, say, fix an origin here and then measure all of these displacements relative to that origin. We found, I mean, this is obviously very clunky. Even drawing the picture is incredibly clunky to do. And so instead of doing that, we said, okay, forget fixing this origin, let's look at just the displacement of each one of these masses. Delta 2, delta 3, delta 4, etc. And everything was so much easier to do in this way. And so the question is, of course, can we do this in general? So, like I said, we first have to sort of establish some sort of ground rules. And in particular, first and foremost, we're only going to ever consider conservative systems. So, conservative systems only. There's a couple of different ways to say conservative systems. One that we saw in the past was that we could write our force in this way, minus grad u. And this just ensured that work was path independent. Work is path independent. Meaning that, you know, if I start here, I'll use a different color, how about? So if I start here at point A, and I want to go to point B, and there's some force acting on me or whatever, no matter what path I end up taking, you know, I can do some weird, crazy paths, but all of them will always end up doing the same amount of work. So what's another way of saying this? Another way of saying this is that if I start and stop at the same point, so say I am always considering ending where I began, again, I can follow these crazy paths, whatever. I could also just stay standing still. I'll always do zero work to get there. Meaning that if I put some effort, we'll say, in sort of hand-wavy terms, if I put some effort into going along one part of that path, I get that back. So if I walk up a hill and then I walk down the hill, it's easier going one way than going the other. In other words, the work that I put in to get up the hill, I get back by going down the hill. This is sort of the notion of conservative forces that we have in general. So, something that's a little bit more obscure is that for a conservative force, our potential energy can only be a function of our position variables. So why is that? Say it isn't. Say we have some potential energy, which is a function of, we'll say, velocity and time. Now, position and velocity can also be implicit functions of time, so I'll write that as well. And this is gonna give us a little chunk of notation that will be useful in the future as well. So I can write down the total energy as 1/2 m vi plus u x, I'll call this L, v L, where I'm using the summation convention. Just for those that don't know, if I write something like this where I have an index repeated, this automatically implies that I'm summing over that index. There's going to be a few times in this where I suspend the summation convention and I'll say explicitly that these are not summed. So just sort of keep that in mind, that this just sort of assume that the summation convention holds unless I say so. If I say that I'm suspending it for an expression, then then you don't sum over indices in that case. But every other case will sum over indices. Okay, so what does it mean for energy to be conserved? Well, that just means that my energy doesn't vary with time. So I can write that out as just 0 is equal to 1/2 m d by dt vi plus du dt, where this is a total time derivative. Total time derivative. Not a partial time derivative. And the difference is very simple. So say I have a function, which is a function of a t, where a depends on t. A total time derivative is going to be defined as the limit as, I'll call this delta t, goes to 0. And I'm going to allow both the t in here and the t in here to vary. Okay? So f of a of t plus delta t and t plus delta t minus f of a t all over delta t. So that's what I mean when I'm talking about a total time derivative. So I allow everything to vary. So I even when something implicitly depends on time, the time varies there. Now, when I write a partial derivative, that is similar, except in that case, I only allow explicit dependencies on time to vary. So, in particular, that's going to look something like this. Over delta t. So notice that in here, I'm not varying time. You can sort of think about it as, and later on, this is sort of the language that I'll use, that if I treat a as a separate coordinate, I fix a. I don't allow a to vary in the partial derivative, but I do allow a to vary in the total derivative. So that's this point of notation that I want to get out of the way because it can be a bit confusing. So if I use this formula, I can expand a out in terms of delta t and everything, assuming delta t is small. And this is just sort of a exercise in Taylor series expansions, but at the end of the day, what you'll find is essentially a modification of the chain rule. So I get something in terms of partial derivatives, and I'll write dA dt as a hard derivative, but it doesn't matter too much because a only depends on time. But just to be consistent, I do allow a to vary in this case, so I use a total derivative on a. And then this is plus the partial derivative of f with respect to t. Okay, and actually this is going to be a very important thing. I'm probably not going to use it a whole lot today, but later on down the line, this is an important thing to remember, that this sort of modified chain rule exists when I have something which is a function of multiple variables. Okay, so anyway, using that, I can write out du dt. Remember, we're assuming that u is some function of position, velocity, and time. So where position, hopefully you can still see what I'm writing. Yeah, so position is a function of time and velocity is a function of time. So I have to use this chain rule. So what I'll find is that this is equal to du dxi dxi dt plus du dvi dvi dt, and then plus du dt. Yeah, so Watcher says that I could also write that dt is 1, and this isn't really a generalized chain. Yeah, you're exactly right. This is just essentially the chain rule from multivariate calculus. But yeah, you're completely correct. So okay, so now I combine all of this stuff together, and so I just look at this equation, use this guy here, and what I find is that for a conserved force in this case, if I just write out dvi dt as the acceleration and dxi dt as the velocity, I find mai plus du dxi times velocity plus these extra terms, I du dt equals 0. Okay, so now here's kind of the point that I'm getting to. We've already said that this has to be 0, because otherwise, it's this argument that I was talking about earlier. Otherwise, work wouldn't be path independent. This is the only way. This expression here is the only way that I get a path-independent work, meaning that if I put in some effort and then go along and back to where I began, I get all of that effort back. So I already know that we're requiring this to be 0. So then I get an extra equation which tells me that this must also be 0. But now let's take a second to think about this. How many degrees of freedom do I have? And when I say a degree of freedom, that just essentially means that if I fix everything else in my system, can I wiggle something in a particular way? So if I have just one particle in 3-dimensional space, I have 3 degrees of freedom, right? Because it can move in all 3 directions. If I fix it in the x direction and the y direction, I can move it in the z direction still. And same thing. So I have 3 degrees of freedom. So in this particular case, if I just have a particle, this gives me 3 equations. This one requirement here gives me three equations. 3 equations for 3 degrees of freedom that will uniquely determine the evolution of this particle, which means that I've already uniquely determined that. So this extra equation won't be satisfied in general unless du dvi equals du dt equals 0. I probably can't see that. There we go. Move that down here. Sorry, it's a little scattered. But, so this is the only way to allow for both of these things to be satisfied simultaneously. And so, you see, this is how we get this requirement that for a conservative force, our potential energy can only depend on position. Depend on, I'll say spatial coordinates. Spatial coordinates. Oops. U equals u of x, xl. Okay? So that's sort of a, it's not a amazingly in-depth argument, but it's a pretty okay hand-waving argument as to why we're only going to consider systems whose potential energy are only functions of position. It's the only systems that we're going to look at. Okay? So here I'll take a quick pause, answer some questions if people have them, and then we'll get into sort of the meat of this and start really tearing into the this sort of generalized formalism. Okay, I'm not seeing any questions quite yet. I'll give it a little bit more time. Doesn't that mean that the sources of the potential are not moving? Sources of the potential are not moving. Not necessarily, because I remember this does not imply that du dt is equal to 0, right? So my potential can still change, right? My potential can still be dynamical, and therefore the sources, and in fact, you can see that this is telling me that the only time dependence that you have, or that the potential energy will have, is from the sources moving. That's essentially what this is telling me, right? Because the only time dependence that can show up in U is from the time dependence in my degrees of freedom. Does that make sense? That's a good question. Okay. Change. Sorry, okay. So the question, I'm not seeing how the potential can change without the potential energy changing. So I'm not really specifying talking about potential and talking about potential energy. Usually you're just multiplying by a constant, say. So you're right, the potential can't change without the potential energy changing. But the potential energy can change, is what I'm saying. Right, so, a simple example is, say, gravity, right? I have two gravitational bodies, say two stars, and actually, in the next stream, I'm planning on going into this more depth. The potential energy in this case is going to be something like gm1 m2 over r. But r is a function of t, right? So as everything evolves and I, solve for the dynamics and everything, I'll get something happening with r, and so u will implicitly be a function of t through its dependence on r. But what I'm saying is that basically the only sort of dynamics happening in the potential energy come exactly from the sources moving. So as my gravitational sources move around, that potential energy changes. But outside of that, if I were to, pin down my sources, then my potential energy would never change. That's what I'm requiring. Okay. Excellent. Perfect. Okay. Glad that helped. Okay, so now that we have sort of our rules of the systems that we actually want to look at, we can move on to actually doing this formalism, deriving a formalism for this. So, just again, as a little more notation, I'm going to specify Cartesian coordinates, because this is something that we're all very familiar with. This is something that it tends to be very easy to write down potentials in Cartesian coordinates. These I'm always going to give the name x. So these are going to be xi, whatever the index is. So in general, this is going to be the name x. It might also end up being something like x, y, z, whatever. Your typical name for Cartesian coordinates. But we also want our formalism in terms of some general set of coordinates. Which I'll call Q, typically. Okay, and just as another sort of notational note, is that a dot implies time, a total time derivative. So dqi dt is just qi dot. It's pretty standard notation, but again, if you haven't seen it before, that's that would be certainly a point of confusion. Okay, and so like we said, we don't want any time derivatives to show up in our potential energy. We don't want any velocities, accelerations, any of that showing up in the potential energy. So we'll restrict to the case where I can write my Cartesian coordinates as in terms of just the generalized coordinates. So not any qi dot, qi double dots, etc. So I don't want any of that showing up in my coordinate changes. Okay? So, let's do this. I've already kind of talked about a degree of freedom and what I mean by that, and I'm going to be saying that a whole lot is how many degrees of freedom do we have? Because as it turns out, for every single degree of freedom, we have to have a coordinate. And this sort of makes sense, because any way that I could have dynamics, I should have a coordinate to describe that dynamics with. So we'll see that there's always a one-to-one correspondence between degrees of freedom and coordinates. So for basically, if I can have a particle moving in any number of dimensions, then each particle I have will give me a degree of freedom for each dimension. And if I have any constraints, each constraint gets rid of a degree of freedom. So say I have two particles restricted to a plane, then that gives me 4 degrees of freedom. Two particles which can each move in 2 dimensions. Now say I go one step further and say these particles, although they can move in 2 dimensions, they're confined to this wire. Right, so these particles can each move in 2 dimensions, but only along this wire. This is what I mean by a constraint. I'm constraining my system to move only in 1 dimension, even though the system itself is 2-dimensional. So in this case, I only have 2 degrees of freedom. Okay? So, excellent. So now hopefully we're all on the same page for the types of systems we're going to look at, the number of coordinates that we're going to need to consider when we have a certain number of degrees of freedom. So, what I'm going to start out with, I'm going to start out by assigning a Cartesian coordinate to every degree of freedom in my system. So, this is sort of under the... Yeah, okay. I'll just say it like that for the time being. And I'm going to write down my energy. Energy in my system, right? Because we've talked a lot about how conservative systems have this dependence on the form of u, so I kind of, for the time being, want to stick to looking at just the energy. And I'm going to write this in kind of a funny way. I'm going to introduce this, really it's a matrix, but this extra object, which I'll just call G. And this is x dot I, x dot j, plus my potential energy, which is only a function of coordinates. Now, there's a very good reason why I introduced this matrix, but in Cartesian coordinates, so Cartesian, this G matrix or the elements of the G matrix are just given by the mass of the ith element times delta ij, where in this case I is not summed. So if you're more comfortable with matrix notation, I might be able to write this as m1, m2, all the way down to mn, whatever my, however many degrees of freedom I have n degrees of freedom, whatever. And some of these masses might be the same, like if I'm moving in 3 dimensions, then I'll have 3 m's repeated for each dimension, but in general, this is going to be the form of this G matrix. Okay? So this is, like I said, this sort of notation is a bit funny, but there's a reason why I want to do it this way. Not only because I personally think it makes things a bit easier to work with later on, a bit more mechanical, but also funny enough because it does have some similarities of what we see in, say, general relativity. But that's sort of besides the point by now. Or for now, because I want to look at what happens if I want to change my coordinates to these generalized coordinates, right? I don't care what the specific form of the coordinates are, I just want a general set of coordinates. Well, looking through this, the first thing that I see are these x dots. So what happens to these x dots? So I want to look at, well, I'll write this as d by dt x I u l. Well, again, I can just apply the chain rule here, where, remember, these ql's are going to be functions of t. So remember, this is going to be dxi dqj times dqj dt. So in a bit more compact notation, I can write this as x dot I is equal to dxi dqj u dot j. Okay? Now, my potential energy is easy. I know that since x is only a function of coordinates, my potential energy is still only going to be a function of generalized coordinates. So I can actually rewrite my energy in terms of these generalized coordinates. Gij, dxi, dqm, dxj, dqn, u dot m, u dot n, plus u of ql. Okay, now this might not seem very enlightening, but I'm gonna sort of employ a bit of a trick. And the trick that I'm going to employ is I'm going to just define a general G matrix. So a G matrix in general coordinates, which I will define by its transformation properties. So if I were to go from some set of qi's to some new set of q's, I'll call q prime, I want gij, which in principle can be a function of these q's, to transform in the following way. Q prime, ij, q prime l, dq prime, I, dqm, dq prime j, dqn. Okay, so you might be asking, okay, why the heck are we doing this? Why are we bothering? Well, because, so what I wrote as just g here is really g ij of x. It just doesn't have an explicit dependence on our Cartesian coordinates. So what happens when I transform and I go from xl to ql, I get a new g in terms of these coordinates. And I'll just go ahead and actually plug that in, right? Because I have specified this transformation property. So I'll write this. This is going to be 1/2 gij, and this is going to be gij of q, right? Because remember, I'm going from x to Q. And then I just plug in this transformation property. This is going to be Q dq, yeah, dxm. Actually, I want to rewrite which of these indices are which. Sorry. Yeah, sorry, I messed up the indices here. My apologies. Did I? Yeah. Yeah. The indices here were messed up. Sorry about that. This should be mn. This should be I, J, mn. Like that. Sorry about that. So this should be mn. This should be mi, dqn, dxj. Like that. And then I have dxi, dqn. Again, I need more indices. This is always a problem we run into with index notation, is we run out of letters to use. So I'll say k and s, q dot, k, q dot, s. Remember, what I call these indices isn't all that important because they're all summed over, so I can kind of call them whatever the heck I want. So the fact that, these indices here don't necessarily have the same name as down here isn't really all that important. But now, let's look at something. If I look at the product of these two things, I have something like dqm, dxi, dxi, dqa. Well, this is just essentially backwards chain rule, right? I know that when I have something like this showing up, it looks like the chain rule. And in fact, I can rewrite this just this way. And you can see that if qm is in fact a function of x, I can rewrite what's on the right-hand side in terms of what's on the left-hand side. But this, if the q's are the same, this obviously gives me 1. But if the q's are different, so if I have, say, dq2, dq1, this is going to give me 0. But if I have dq1, dq1, this is going to give me 1. So this is just a Kronecker delta between these two indices. Right, because the second coordinate has no dependence on the first coordinate. But the first coordinate is the first coordinate, so that just gives me 1. Hopefully that's clear why this gives the Kronecker delta. But you can see that I can combine this and this to give a Kronecker delta, and I can combine this and this to give a Kronecker delta. So, in doing that, I get that my energy is equal to G, I'll call this Mn, QL, Q dot M, Q dot N, plus U of QL. And you see, this has exactly the same form as what it had before. Right? It sort of almost artificially has the same form because we defined this transformation property specifically so that it would keep its form. But nevertheless, this is useful because I can now always, without fail, I can always write the total energy in this form. And that's no small feat, right? I can choose any set of coordinates, and I can always write the energy this way. I just need to find U, or find G. Find G. So as long as I can figure out the elements of G, I can always, without fail, write my energy in this way. But G isn't actually too difficult to find, because as long as I'm starting from some set of coordinates where I know the form of energy, so say Cartesian coordinates, I can always just do coordinate transformations to get to some new set of coordinates. But I know how G transforms. So I can always find G in any set of coordinates just by applying this transformation rule. Okay? So this is sort of like the key point, is just sort of by looking at how things transform allows me to do things in a very coordinate independent way. So another way of writing this is that this combination GMN UL dot UN dot, this is equal to, if I change coordinates to some Q prime L Q dot prime M Q dot prime N. These two things are equivalent. So again, like I said, if you have some experience seeing stuff in general relativity or even special relativity, this might look a bit familiar to you, because G behaves, it's not exactly, but it's very similar to a metric tensor. But again, that's sort of, besides the point, and sort of more than I want to get into right now, but that's sort of what I mean by this. This certainly ties into general relativity, which of course shouldn't surprise us, because general relativity, a main goal of that is also to find a formalism of physics which is entirely independent of our coordinates. So it shouldn't really surprise us that we see some similarities popping up. Yes. So as Narf pointed out, you'll often hear people say that a tensor is something that transforms like a tensor. Well, this is what they mean. This is how a tensor transforms, in particular a covariant tensor. But again, this is sort of beyond the scope of this lesson. I don't want to get into covariance, contravariance, upper, lower indices, all that stuff right now. But down the line, we will, and all of this discussion will be very helpful. So here I think I'll take a quick break. And then I'll go through sort of an example to see how these all work, and then we'll continue on. Okay, so feel free to ask any questions and all that. Take a drink of some water. Okay, not seeing any questions popping up, but if you think of any, feel free to leave them there. I think I'll go on, though. So, just one sort of important property of these G's and this is something that we can find by just looking at this transformation property, is that if you look at it, if I flip the order of these indices, it doesn't change anything. I get exactly the same thing, right? You can sort of see it as I'm taking derivatives of only q's in this transformation rule. And so the end result of that is essentially that gij is equal to gji. And this is actually quite helpful because this means that, we only have to find a little more than half of the total number of elements of G. So we'll use this to our advantage later on, but this is a very important property to talk about. So let's go ahead and look at an example of essentially finding these G's. So say we have two particles. I'll call them particle 1 and particle 2. And they're free to move in 2 dimensions. So they're restricted to a plane, but they're free to move in 2 dimensions. So we will call the Cartesian coordinates of each of these x1 and x2. So say I have some Cartesian axis here, stretches out x, y, then the position of this guy I'll call x1 and y1, and call this guy x2 and y2. Now remember, in Cartesian coordinates, so I'll write this gij of x. Remember, x is always my shorthand for Cartesian coordinates. This is mi delta ij, with I not summed. So I only ever get diagonal elements to this guy because of the Kronecker delta, and those diagonal elements are always going to be the mass. So in particular, gx1, gx2, gx1, gx1 is going to be equal to gy1, gy1, and that's just m1. And then gx2, x2 is equal to gy2, y2, which is m2, which I'll just write as gxi, xi is equal to mi. And this is also equal to g, y, I, where I is equal to 1 and 2, and it's not summed here in this particular expression. So in Cartesian coordinates, I can write my non-zero elements of G in this form, and all of the rest of the elements are going to be 0. So I'm not going to write all of them out, but yeah. So now let's say that for whatever system we want to describe, it's more convenient to us to talk about it in terms of polar coordinates. So in that case, each of these guys are going to be written as xi is r cosine phi, and yi is r sine phi I, where again I is not summed. Yeah, I told you there'd be a lot of bouncing back and forth between summing over repeated indices and not, but I promise it's still easier to use the summation convention. Okay, so now I want to find G in these polar coordinates. So if we remember our transformation property, when I start out, so G, we'll call it GMN, and our old coordinates, which I'll call QL, are given is given in terms of new coordinates as I'll call q prime d q this is qi dqm dq prime j dqn. So I just have to find these derivatives where my new coordinates are the r's and the phi's, and my old coordinates are the well, actually, I want to find the elements of G, so I'll say that G unprimed of R and phi, R sub L, phi sub L, this is going to be given in terms of Cartesian coordinates as G sub ij of x sub L, y sub L. And then I just apply this rule. This is dxi d, well, q m d x j dq n, where here x, I'm being a little sloppy with notation admittedly, but in this expression x can be either x or y and q can be either r or phi. So we just have to take derivatives of these expressions with respect to r and phi, is sort of the end moral of the story. And we really only have to take 4 derivatives, which are easy enough to do. So we'll start by taking the derivative of this expression with respect to r's. And you see that this is only going to be non-zero if the I on the left-hand side and the I on the right-hand side are the same. So x1 is given in terms of r1 and phi1, not r2 and phi2. So that's going to give me a Kronecker delta. So this is going to be cosine phi I delta ij. So this is only non-zero if these two values are the same. And I can keep doing this. d phi j is equal to sine phi I delta ij. Come down here, dyi drj sine phi I delta ij. And then finally, this guy should be minus, I think there should be an r here. Sorry, I messed this one up. This should be minus r sub I, and this should be r sub I cosine phi sub I delta ij, where again in all 4 of these I is not summed. Okay, now we just have to find the elements of G using this transformation rule. And like I said, this is all sort of mechanical at this point. We just take derivatives, we plug them into the transformation rule, and we get our expression. So I'll say G prime RK RL. I'll write this L. I'm going to explicitly write the summation symbol in this case. And this is GXI XI dxi drk dxi drl plus gyi yi dyi drk dyi drl. And, you know, working through the details, if you want me to go through them, you can, feel free to, or I can do that, feel free to ask. But like I said, this is all sort of turning the crank, doing some algebra, working through it. And this gives me just mk delta KL, where, again, in these lines here, I'm not going to be using summation convention at all. So if I'm summing, I write the summation explicitly. So the other one that we find is RK phi L is equal to, remember I said these are symmetric. And we do the same thing here. G, xi, 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 drk, dxi, d phi L, plus gyi, yi, dyi, drk, dyi, d phi L. And when you plug everything in, these go to 0. And one last one that we get, phi k, phi L. And I'll just write it here. This gives you m sub k r sub k squared times delta KL. So, what happens? One thing that we can notice is that in the elements of G, we can see that our coordinates show up. R sub k appears in our actual coordinate, or in our actual G matrix in this particular case. And in general, it will. In general, G will depend on our coordinates, but only our coordinates, right? Because the transformation only depends on how coordinates depend on coordinates. And since we're restricting ourselves to the case where coordinates only depend on other coordinates and not derivatives, we're never going to get any extra time derivatives showing up in G. In particular, our kinetic energy term. Okay, so all that said, I know that I can write my energy as G prime Mn of my Q's, U dot M, U dot N, plus U, UL. And so now I just plug this stuff in. So you can see that it's only going to be non-zero when my Q dots are the same, because everything still is always proportional to my Kronecker delta. And just plugging stuff in, I get something which looks like this. M2 R dot 2 squared plus M1 R1 squared phi dot squared 1 plus M2 R2 phi dot squared 2 plus my potential energy. And there you go. We've written our total energy in these new coordinates. And here we see sort of we begin to see sort of the magic of doing things in this way. So we get the kinetic energy associated with radial motion. But on top of that, we for free, again, like I said, it falls out of this formalism, the rotational kinetic energy as well. In particular, this energy that I write is always the total energy, which means I don't have to bend over backwards and do a whole bunch of gymnastics like we did in the Newtonian formalism to find these expressions of rotational kinetic energy and, as we'll see, angular momentum, things like that. We get those expressions for free because we must include them. We have no choice but to include them. So this is sort of the beauty of this formalism, that we get all of this stuff just by sort of turning the crank, doing everything very mechanically, and all of this falls out of the formalism. Okay. So now I think we'll take another quick break, And then we'll actually derive the equations of motion associated with this. So if anybody has any questions, feel free to ask them. I'll wait a few minutes and then continue. And the cues represent something other than position. Yes. Yes. So, okay. I shouldn't be so quick to say yes. It sort of depends on what you mean by position. So they will typically be some sort of spatial coordinate, but it doesn't have to be some set axis. So and we'll see more of this in particular in the next stream, but so one coordinate which tends to be very useful to use is a relative distance. So if I have two, again, actually let's go back to our two stars, which are gravitating, and say I want to work in a system where one mass isn't necessarily way bigger than the other mass. So in principle, both of these are going to move. Fixing my coordinates, like I said, with an origin here, whatever, and defining distance vectors, all that, is very, very clunky. And in fact, what's much simpler to use is just this relative distance here. So if I'm understanding your question correctly, the cues can certainly be something other than an absolute position. They can be some relative position as well. And so sort of, if I go back to this picture that I drew earlier of some, wild wire and put a bead on that wire, my cue could represent, the position on this bead that this guy is at. So this could be my cue, like that. It can follow the wire. Again, if I have a way of expressing, if I can write the coordinates in this way, then they're perfectly fine coordinates to use. So I think that's how I understand what you're asking, is if it's an absolute position, and certainly not. It does not have to be an absolute position, if that makes sense. And like I said, I'll show more of this in my next stream. This one is more meant to, derive the equations of motion and all that stuff that we can use in the future, because I didn't want this to turn into a 5-hour stream. Okay, so it was more thinking something like velocity or momentum. So this goes back to what we were talking about before, which is we are not considering the cases. We're not considering any case where velocity or momentum or anything shows up anywhere besides here. This is the only place where these terms will ever show up for a conservative system, and that's the only place we ever want them to show up. So, in particular, we don't want to write something like some qi is equal to qi, which I can write in terms of qi prime, q dot prime, etc. I don't want this. We are explicitly staying away from this sort of thing. I mean, in general, I would have to think about how you would do that, but it would get very, very messy very quickly, and you'd have to make sure to not introduce any new degrees of freedom, right? Because the only degrees of freedom that you have in your system are fixed, right? So I can call position my degrees of freedom. I could call my I could also call my velocity a degree of freedom if I wanted to, but we're essentially choosing to use positions as our degrees of freedom, if that makes sense. Sorry if that doesn't fully answer your question. I think that the correct answer to your question is I'm not exactly sure. It's just that, that adds a lot of complications if you try to do it that way. So we tend to stay away from doing things that way. Exactly. Okay, so now we're kind of starting to see how how all of this stuff might be very useful, but we still haven't gotten any physics out of this, really. We haven't found any equations that determine how things are going to move in our system. So that's what I want to do next. And in particular, if you remember way, way back to one of my first streams, if you've seen it, we derived the Newton's laws, so the equations of motion for a system, in terms of momentum. And in Cartesian coordinates, this is just pi is mi x dot I, where of course I is not summed. Okay. So, as I was just saying, to answer the previous question, the only x dot dependence we'll ever have in our energy shows up right here. That's the only place that, well, not just x dot, but also any q dots or anything are ever going to show up. So for Cartesian coordinates, I can pretty safely rewrite this as just dE dxi dot. Remember, this is for a conservative system. This isn't going to be true conservative in general. But as long as the system is conservative, no x dot dependences show up in U. This is perfectly fine to say. And I'll rewrite this as g sub ij x dot j. Again, this is Cartesian. So now when I do a coordinate transformation, so now say I want to take xi and I want to replace it with some qj. Well, the right-hand side of this transforms, and we know how it transforms. Our g is going to transform like this. ul dqm dxi dqn dxj. And I will say you do have to be a little bit careful with these transformations, but I'm kind of just writing them down. If you're very careful, this is the stuff that you'll end up with. But so I'll say that if I will warn you that if you do end up trying to do this all yourself, be very, very careful about what goes up top, what goes up bottom when you're going from some set of coordinates to another. It can get a little bit hairy to keep track of all of that, but just double check to make sure that you're doing all your bookkeeping right, I guess. So now you see that I end up with a delta or a Kronecker delta here. So this is going to be delta nk. And this is going to give me something like dqm dxi g prime mn of ql q dot n. So now what I'm going to do, I'm again going to define something. I'm just going to just give something a name. And this is I'm going to say a generalized momentum. This is also typically called a conjugate momentum to Q. Qi. And that's given by E sub I. Whoops. E sub I is equal to G sub ij Q sub L Q dot sub j. Where now I'm back to using the summation convention. Okay. This is great. It's important, and in particular, what you'll find is that when I go through this, I can, if I change my coordinates, qi goes to qi prime, just the same thing I found up here. My momentum is going to be dq prime j dq I d j prime, where now this is the pj corresponding to the q prime i's, or whichever way you want to say it. But that's just from this same doing these transformations, working through them, and this is the transformation rule that you get. If you like your names, this is a I believe this is transforming as a covariant rank 1 tensor, whereas the Q's transform as a contravariant rank 1 tensor. But whatever. That's for those that are interested. That's the naming, but whatever. Not super important. Now, I can rewrite this in terms, so essentially solve for qj, and I will do that in terms of a new object. I'm going to introduce a new object that I'm going to call g inverse. Q dot I equal to g inverse ij q l e j. And I define G inverse so that GIK, G inverse KJ, just gives me a Kronecker delta. So you can see that if I take this expression and I multiply both sides by G inverse and I sum over one of the indices, I get exactly this. Okay. So in particular, in Cartesian coordinates, this G inverse is going to be, so remembering that Gij, call this x, is equal to mi delta ij. Using this expression here, it's fairly straightforward to see that G inverse ij xl is equal to 1 over mi delta ij. Okay, this is another one that I'm gonna put in a box. And actually, while I'm boxing everything, I might as well put this one in a box as well. That's going to be very, very important. Okay. Now, I have this Q dot in terms of G inverse and P, which means that I can re-express my energy, essentially get rid of the q dots in the energy expression by just replacing them with this here. So I'm going to do that. And when I do that, I get something like 1/2 Gij QL, and then I replace the q dots. So this is G inverse Ij QL E J. Oh, shoot. To be careful. Indices M G inverse J N QL E N plus U of QL. Now, again, remember this expression here, and you see that when I pair up, I mean, I could pair up either one of these, but one of these is going to combine to give me just a Kronecker delta. In this case, it's a Kronecker delta with I and N. I can rewrite this as 1/2 G inverse, I believe M N, E sub M, E sub N. I'll explicitly write this as a function of Q's. P sub M, P sub N, plus U sub L. And I'm going to give this expression a very special name. P sub L of H J U L I P J plus U L. This here, when I express my energy in terms of P's and Q's only, so no Q dots, no P dots, no anything like that, this is known as the Hamiltonian. And from this expression is what we'll use to get all of our equations of motion. And actually, one of them we can already write down. We can write down one of them just by looking at this. So what we've done by writing everything in terms of just P and Q is we've eliminated Q dots from our expression of the Hamiltonian, and so we can sort of consider the P's and the Q's as completely separate things. And what we'll do is we'll write down a set of differential equations, which then couple them back together, or essentially relate them back to each other. And so the first one that we can write is that the change in Q is given, you see, if I just take a derivative of H with respect to P, I get exactly what I wrote up here. So our first equation of motion is that Q dot I is equal to dH dP I. Okay? This is equation number 1. Equation number 1. Now, equation number 2 is going to be a little bit trickier. Well, yeah. So this is our first expression. Now, okay, the second equation is going to be a little bit trickier to find. And we might be tempted. So we know, looking back, we know that Fi is equal to dPi dTi. Whoop, oh, not Ti. And this is d minus du dxi. Right? This is just a restatement of F equals minus grad U. We know this is true for conservative systems. So we might guess for P sub I dot that this is just going to be minus du dqi. We'll guess this. But it's not so easy to, it is actually very easy to see the case where this fails. And to see it, we'll just consider a single particle in 2 dimensions. Which should immediately tell us that we should have 2 DOFs, 2 degrees of freedom, and 2 coordinates. Now in Cartesian, it's easy to write down my Hamiltonian. xi pi. This is going to be 1 over 2m, right? Because like I said, in Cartesian coordinates, it's just 1 over m times the Kronecker delta. And this is p sub I plus u sub xi. Okay, so now let's switch to polar coordinates. Let's just look at this in polar coordinates. Just, hey, we're free to mess around with our degrees, with our coordinates. So let's just play around with this. We see that this does work in this particular set of coordinates, right? This is fine. But what happens when we switch to polar coordinates is very interesting. So something that we already found is that when I write my energy, again, going back to the energy, not the Hamiltonian, phi dot squared plus u of r comma phi. I can find my conjugate momenta by just, like I said, taking derivatives of the energy, dr dot, because we're guaranteed to only ever have a q dot dependence in the kinetic energy terms. And so this is going to give me mr dot, but it's also going to give me e phi equals de d phi dot, and this is mr squared phi dot. And just as a quick side note, we see that this is not an actual momentum. It's not a momentum in the same way that this is a momentum. In other words, it's not a linear momentum. This is in fact an angular momentum. So again, we didn't necessarily have to have anything spinning. We didn't have to go and look at cross products and nonsense like that. We, for free, get angular momentum as part of our analysis. Guaranteed to have it in our analysis. And so this is sort of a common theme, is that these conjugate momenta aren't necessarily going to be linear momenta, but they're going to be important quantities nonetheless. Okay. So anyway, we can solve this, right? We know that q dot is equal to g inverse ij q dot I ej. We know that r dot is equal to p sub r over m, and we see that phi dot is equal to p sub phi over mr squared, and this gives us our elements of G inverse. There is another way of finding the elements of G inverse that I'll show you after this example, but this is one way of doing it. So this is just 1 over m, and inverse phi is equal to 1 over mr squared. And all others are 0. Okay? So now I write down my Hamiltonian in terms of r and phi. And this is p r squared over 2m plus p phi squared over 2mr squared plus whatever my potential energy is. Okay, now here's the kicker. If I were to just look at this guy naively, well, I know that, so I just found that p sub r is equal to mr dot, correct? So the time derivative of pr is just going to be proportional to the acceleration in the r direction, right? Now, let's think of a system where we have, I don't know, some object being experiencing some force that makes it go around in a circle of radius r. So in this case, r of t is fixed, right? Which means that r double dot is 0. But going back to classical mechanics, we know that, well, the force equals du dr, evaluated r equals big R. This is not equal to 0. And in fact, this is going to be equal to the centripetal force. Correct? So this is going to be mv squared over r in this case. We know that. We've already found that. We've already dealt with that with Newtonian mechanics. So if I just say that p dot is equal to minus du dr, this is obviously wrong, because I find that the left-hand side is 0 and the right-hand side is not 0. So this can't be the case. But we should almost expect that to not be the case. Why? Because this guy here. We're not taking into account the fact that coordinate dependences, when we're not working in Cartesian coordinates, can show up elsewhere besides the potential energy. So let's make another guess and do something similar, but this time take into account the full coordinate dependence of the Hamiltonian, and write down something like this. EUI. Now let's see what happens. So again, we find that P sub r is equal to mr P dot sub r is equal to mr double dot. Now, in this case, if I just take the derivative of the Hamiltonian with respect to r, this first term gives me minus p phi squared over 2mr cubed plus du dr. So let's write that down here. Put a minus sign here. Sorry, dropped that. This is equal to p phi squared over mr cubed minus du dr. Now if I evaluate this at big R, at r equals big R, the left-hand side is 0. This is equal to p phi squared over mr cubed minus du r. Sorry, this should be big R. Big R cubed. And this is equal to 0. But this is exactly what we found before. du dr, r equals r, is equal to p phi squared over mr cubed. If I rewrite p phi squared, I get something like, well, I can just scroll up and we can see that p phi is mr squared phi dot. So if I square this, p sub phi squared is m squared if I evaluate it at big R. I get something like this. And so this becomes m big R phi dot squared, which I can rewrite as mv squared over R. So we see that this is perfectly fine. This works out grand. We get exactly what we expect. Now, one other thing to notice about this is that I'm just going to rewrite this equation. So p dot r equals mr double dot is equal to p phi squared over mr cubed minus du dr. Here we see something actually I personally think is very cool, in that if we just, interpret this as a one-dimensional force, right, which is essentially what it is. It's mass times an acceleration. On the right-hand side, we have what we would typically expect from our radial force, but we also get a second force. It shows up as a force, which acts in the outward direction, right? So in this case, if I'm going around in a circle, I get this force, which acts inwards, and this is my du dr. This acts in the inward direction. It's trying to decrease my radius. But I also get a second force, which is outwards. p phi squared over mr cubed. And these two are fighting each other. So I get some force coming from the fact that I have some angular momentum, and then the force that's just trying to pull me in. And you can see that when these two perfectly balance, I get no acceleration in the r direction, and I get something moving in a circle. So all that to say, what we've done is we've compensated for the fact that we have some angular motion by including an explicit centrifugal force. So this is a centrifugal force, not centripetal. It's outward directed. And it shows up. It comes out of the math. It's a real force that shows up. It counteracts the externally applied force. And it's perfectly fine. So here's an example that shows you that a centrifugal force is not a fictitious thing. It's something very real that shows up. Otherwise, something couldn't travel around in a circle. Okay. Now, I'm gonna talk about one quick thing, and then take a break, and then do a quick example, and then be done for today. So, okay. When I wrote down my Hamiltonian, this is in terms of Q sub L's and P sub L's. 1/2 G inverse Ij U L Ei Ej plus U UL. So now, just like before, this is true in any set of coordinates, just like what we found for the energy. Now, for the energy, all I had to find were the elements of G, and I could write it in any set of coordinates. So in this case, all I have to find are the elements of G inverse, and I can write down my Hamiltonian in any set of coordinates that I want. So to do that, we have to know how G transforms. So we'll start by looking at q dot I, this expression here. Ij inverse ql p sub j. Now we know how q dot transforms. We know how pj transforms, so we should be able to find out how G inverse transforms just by requiring that the left-hand side of this equation and the right-hand side of this equation transform in the same way. So in particular, q dot I is qi q prime j, q dot prime j. I'm going to move this over a little bit. Pi is dq prime j dqi pj. And then I can write the backwards transformations of these. This should be prime, sorry. So I can rewrite these as, I'm really writing the same thing, but just sort of for clarity, I'll rewrite these as sort of the backwards of what I wrote on the left. So then this is pi prime dq j dq prime I pj. So really I just wrote down the same thing twice, just putting primes in different places. Okay, so now I'm going to transform, well, I'm going to just transform the left-hand side of this equation first. In that case, I get that dqi dq prime j times q dot prime j is equal to G inverse I j ql e j. Okay. So now I want to transform both G inverse Ij and P and Pj, and require that the transformation is the same as the left-hand side. So I'll write that in this case. G prime inverse, running out of indices, and then G prime inverse, sorry, I just want to make sure that I don't screw anything up here, P prime K. But I know what P prime is in terms of P, so then I know that G inverse Ij ql pj is equal to qi q prime j, and then I transform P prime d q, I don't know what index should I use here, say s d q prime k, and this is times G prime inverse, I believe this is J K E prime L E sub S, if I did that correctly. Okay, and actually I'm gonna get rid of these parentheses. And you can see that this is satisfied if G inverse Ij ql is equal to dqi dq prime j dq S, sure. dq prime k. This should be is. G, jk prime inverse q prime l. And so we found how G inverse transforms. So, yet again, now that we know how G inverse transforms, we can always find our Hamiltonian in any set of coordinates just by finding the elements of G inverse. In particular, if we start from Cartesian coordinates, this just becomes G, and this is one that we'll use quite often because things are pretty easy, or the Hamiltonian tends to be pretty easy to write down in Cartesian coordinates. So this is going to be dqi, dxk, dqj, dxk. So if I start in Cartesian coordinates, I can find G inverse just by doing this. Otherwise, I can use this transformation instead. Okay. So I'll take another quick break. If anybody has questions, please feel free to ask them. And I'll end things off by, it's a very simple example, but it's just one of these, sort of seeing how things work. In the next stream that I do, I'm planning on doing, going more in depth into more complicated and more interesting systems than just this, but yeah, if anybody has any questions, more than happy to answer them. If not, can move on. Well, not seeing any questions at the moment. So I think I'm gonna go ahead and get through this example and then wrap things up. So, okay. So let's go ahead and consider a very simple example where I have a bead on a loop. And I'm going to hold this loop vertical so that I get some force due to gravity acting downwards on this bead. I'll say the bead has a mass m, and it's constrained to move on this loop. So how many degrees of freedom do we have? We only have one, right? It may initially look like this bead can move in 2 dimensions, but it's constrained to moving along this loop. I essentially have 2 degrees of freedom, but 1 constraint, which leaves me with only 1 real degree of freedom. But that's not going to stop me from writing my Hamiltonian, and I'll start with the Hamiltonian in Cartesian coordinates. So I'll call those x and y, and we know that the potential energy is just mgy. So h, is going to be a function of x, y, px, py, and we know its form in Cartesian. That's just this, py squared over 2m plus mgy. But I can't forget that I also have a constraint equation. And my constraint is just that the coordinates always have to be related in this way. No matter how my bead moves, it's never going to move off of this loop, where r is the radius of the loop. I probably should have written that. Okay, so these obviously aren't the most convenient coordinates that we could be using. We have this really nice symmetry of this circle, and we aren't using it at all. So let's switch to a coordinate system which does use this, namely polar coordinates. So what we'll do, we will measure where the bead is from its angle to the bottom. So we'll call that phi. Things are getting a little bit messy there, so I'll redraw this. And I'll say that, I did a bad job of not drawing that at 90 degrees, but I'll call that angle phi there. So, if we spend some time taking a look at this and everything, since it's measured from the bottom of this loop, I want to call x r sine phi, and y is equal to minus r cosine phi. Y is minus just because I've called this direction the positive y direction. And so the positive cosine phi direction points this way, so I get something which is negative there. Okay, so now all I have to do is find g inverse phi phi, because that's my only coordinate now. Notice that by writing it this way, I've written x and y in terms of only a single coordinate, which has essentially made my constraint equation redundant. So the magic of this sort of generalized system is that I can basically choose a set of coordinates where constraint equations are unnecessary. And in fact, I could choose any one parameter that I want such that this constraint equation is satisfied. So that's something that's really nice about using this generalized framework. But in particular, actually, I'm just going to write down g phi phi. This is easy since we only have a single degree of freedom. So this is g phi phi, not g phi phi inverse. And just by what we did before, this is going to be given by y d phi squared, which is mr squared. And so now g phi phi times g phi phi inverse, well, since I only have phi's, this should just be 1, which automatically tells me that g inverse phi phi is 1 over mr squared. So now I just go ahead and write down my Hamiltonian using this, phi p sub phi. This is equal to p phi squared over 2mr squared. And then minus, well, y is given here, so I know this is just minus mg. sorry, mgr cosine phi is my potential energy. Excellent. So now all I have to do is use my Hamilton's equations. So I'll write down Hamilton's equations in general, just really quick again. So q dot I is dh dpi, and then pi dot minus dh dqi. And I'll go ahead and write these in a box. So now I can write this as, well, phi dot is equal to dh dp phi, which is p phi over mr squared. And so, of course, I can rearrange this and find that p phi is mr squared phi dot. Again, this is an angular momentum, not a linear momentum. So now I use this second equation, p dot phi. Well, I can take the time derivative of this equation, and this gives me mr squared phi double dot. This is minus dh d phi, which, if I'm not mistaken, should be minus mgr sine phi. Simplifying everything out, you get that phi double dot is equal to minus g over r sine phi. And there you have it. There's our equation of motion. Didn't have to talk about, we didn't have to explicitly look at angular momentum. We didn't have to do any funny trigonometry. We didn't have to do any of that. We just changed our coordinates, took some derivatives, plugged them in, and then there you go. We wrote down our equation of motion. And of course, we should have expected this equation of motion. This is just what we get for a pendulum. Unfortunately, this Hamiltonian framework won't help us solve this equation, since this is still horribly transcendental, but it's very convenient that we now just have a formalism where we don't have to do these mental gymnastics. Now the hardest part of this equation, or of this process, is just finding a good set of coordinates, and then relating those back to whatever coordinates we know how to write the Hamiltonian in terms of. That's going to be the hardest part of things. Once we can do that, we just turn the crank, and we get our equations of motion, which we can then solve using whatever tricks we want to solve the equations of motion. So that's sort of the whole beauty of using Hamiltonian mechanics. And I think that's really all I have for today. So anybody has any, I guess, closing questions or anything, I'd be more than happy to stick around for a bit, a few minutes, and answer them, but yeah. Hopefully it's sort of a, I don't really expect this particular example to be super awe-inspiring, that this is the best framework to use, but as we dive into more and more complicated examples of this, I think that you'll start to agree that this is a very nice framework for classical mechanics. And actually, you can prove some pretty interesting stuff in classical mechanics using Hamiltonian. It's not quite as powerful as some of the stuff you can prove with Lagrangian mechanics, but like I said, the Lagrangian mechanics is much less motivated than this. Okay. Narf says that he gets the payoff is worth it, but churning through these transformation rules is rough. Yeah, I agree. I agree that these transformation rules, they can be a bit of a pain to deal with, but yeah, I mean, I completely agree. At the end of the day, a lot of times a computer program can do this stuff for you, whereas a computer program isn't necessarily going to be good at, coming up with some conserved quantity that, oh, hey, we can actually use this to write down an equation of motion, which is what we often run into with Newtonian mechanics, is that it's not always the most intuitive to see things. But I do agree that the transformation rules are rough. As one of my professors once said, you seem to have a sort of conservation of trouble. You save yourself some work in one place, and then you get those same difficulties show up elsewhere. So you sort of see that here, where we don't have to do as much mental gymnastics to get to our answer. Yeah, we might have to do a little bit more calculus and algebraic manipulation to get to the Hamiltonian. What do I mean by Lagrangian mechanics is less motivated? Lagrangian mechanics is entirely motivated because it gives the correct answer. Right, so I like Hamiltonian mechanics a bit better with what we know now, because of the fact that we've seen how powerful it can be to use a formalism where we don't have to have a fixed origin. And so Hamiltonian mechanics sort of comes very naturally because it's just the Hamiltonian's just total energy. That's like a physical thing that makes a whole lot of sense, and all of that. Whereas, if I don't know how much Lagrangian mechanics you know or don't know, but I mean, when I'm writing down the Lagrangian, I typically write down the action, and this is whatever q dot t. It's very similar in that it's a generalized formalism. This is ql dot t. But the issue is that the Lagrangian, this is my kinetic energy minus my potential energy. So my sort of issue with all of this is that, okay, there's sort of a few reasons why I don't love jumping straight into Lagrangian mechanics, because the question is, okay, what the heck is this action? That's the name of this guy. This guy here is the action. So what does this action mean? What does this Lagrangian mean? This certainly doesn't seem to correspond to anything physical. It's not a total energy. It's just half of my total energy minus the other half of my total energy. So what the heck is that? And so you get Lagrangian mechanics by minimizing this action, I guess, technically extremizing it, but in the case of classical mechanics, most of the time you're minimizing it. And so why? Why do we minimize it? Where does that restriction come from? And the whole motivation is that essentially, yeah, you can use this formalism to get the correct answer, but the Hamiltonian mechanics to me has a lot more like physical motivation behind it, right? We're looking at the total energy of something, and we're just sort of messing around with that total energy until we can do our physics in a coordinate-independent way. Whereas Lagrangian mechanics is very motivated. It is very motivated. But it's motivated as a limit of quantum mechanics. And so I to sort of spoil things a bit, that's sort of the direction that I want to go. I want to sort of motivate everything. So, before I start getting into Lagrangian mechanics, I want to talk about some quantum mechanics first. And then we'll see how Lagrangian mechanics is actually a limit of quantum mechanics. And so all of this action in Lagrangian and all of this stuff is actually very well motivated. Why we minimize it, all of this, when we see the quantum mechanics first. Yes, this is all a lot of foreshadowing. But yeah, so that's sort of yeah, so Lagrange, yeah, I personally think that Lagrangian mechanics and Hamiltonian mechanics are taught in the wrong order. But yeah, I agree. The Hamiltonian formalism makes a lot more intuitive sense. It's a lot easier to grasp, I guess, kind of what we're doing, because we're just kind of rewriting all of what we've done in Newtonian mechanics in a coordinate-independent way. But yeah. So before I spoil everything that I want to do, I think I might wrap it up here. So I'll go ahead and say thanks to everyone who showed up. Thanks for everyone who watches this after the fact. I always appreciate all the support and everything that you guys give me. And yeah, for those Americans out there, or I guess you don't have to be American, but happy July 4th, all that stuff. Yeah, and I'll see you guys next time.